Hello, my name is Emily Ureña, a senior from Jose Marti STEM Academy. With the increasing threats of chemical warfare agent exposure throughout the years, there is a need to innovate and anticipate how these lethal chemicals behave in the air. That's why at the New Jersey Institute of Technology, I targeted my research on the computational analysis of binary mixtures of dimethyl methylphosphonate. My project's initial intention was to investigate chemical warfare agents, or what I will be referring to as CWAs. CWAs, such as sarin, have been outlawed since the 1993 Chemical Weapons Convention. However, their threat to humanity remains present. While individuals tend to believe CWAs are released as gases, they are commonly released as aerosols, or tiny particles of liquid suspended in the air. In this form, they can create mixtures with molecules found in the atmosphere like water, creating non-ideal mixtures with excess properties. Since research on sarin is scarce, dimethyl methylphosphonate, or DMMP, is commonly used as a surrogate. However, DMMP data is also rare, requiring the need for similar molecules to be analyzed for proper analysis of DMMP. My research revolves around the investigation of similar mixtures to DMMP water, allowing for a more accurate and reliable analysis of the target mixture based on various mixtures. With the idea of non-ideal mixtures comes the concept of excess properties. When a mixture is non-ideal, signifying components either do not share similar sizes or interactions, their general properties like volume and viscosity can shift. For our study, the targeted mixtures were DMMP water and DMMP methanol. Due to methanol's similarities to water, we believed it could be used as a way to check if the DMMP water results from the literature data were logical. Since my research was split into portions of literature data analysis and the investigation of the Peg-Robinson equation of state, I will begin with the literature data analysis component. To observe how molecular structure and bonding may impact excess properties, similar molecules to DMMP had to be found. For this study, we used the molecules N-methyldithanoamide, MDA, N-acetylmorpholine, NAM, and dimethyl carbonate, DMC, as our comparative molecules due to their similar size and bonding properties to DMMP. By collecting density and viscosity literature data on each molecule's mixtures with water and/or methanol, I was able to create a Python script to calculate the excess properties for each mixture and plot it. Once all graphs were created, I could now observe how each plot shifted depending on the mixture. These are the equations I utilized to calculate each excess volume and excess viscosity property. For excess volume, most graphs depicted a negative correlation, except for the DMMP methanol mixture. While this could be an error from the literature data's experimentation, another reason for the positive plot could be bonding differences. While water has 2 hydrogen bonding sites, methanol only has 1, causing the DMMP methanol mixture to create globular components that repel each other. While this should repeat with the other mixtures, the only difference between the molecules in DMMP is a phosphorus atom, which may have an impact on how methanol binds to DMMP. For excess viscosity, half the graphs portray a positive correlation, while the rest depict a negative correlation. While there seems to be no organization or trend between the plots, a reason why the graphs may vary so drastically could be because of the particular molecular structure of each molecule. Overall, while excess volume was more dependent on bonds and size, excess viscosity significantly changed for minute shifts in molecular structure. Based on the knowledge collected, since the DMMP water mixture's excess properties depicted a strong attraction between water and DMMP, sarin is likely to show similar results, especially since its fluorine atom has a high electronegativity and therefore is an excellent hydrogen bonding site for water. For part 2 of this study, I investigated the applicability of the Peg-Robinson equation of state, which was able to accurately predict the liquid density of DMMP in a previous study. While the equation is utilized for bulk compounds, an iteration of the equation for mixtures has been made, yet rarely used. For the new Python script to calculate densities, The polynomial form of the equation was used with the application of the mixing rules. After plotting the calculated densities, the script also plotted our study against prior literature data on DMMP mixtures. Strangely, the graph seems most accurate at the 0.5 mole fraction and least accurate at the 0 and 1. However, this is likely caused by the Pegg-Robinson equation of state mixing rules being specialized for mixtures at the 0.5 mole fraction, resulting in these discrepancies. Despite the large difference of values when it came to the pure components, the modified Pegg-Robinson equation of state was accurate in range. However, if the equation can be fixed to accommodate for pure liquids, it has the potential to accurately calculate densities of mixtures without experimentation. For future work, I would like to continue analyzing more literature data on mixtures to create a molecular catalog for the prediction of excess properties, especially excess viscosity. Along with this, I would like to go into a deeper investigation of the mixing rules of the Pegg-Robinson equation of state to examine the possibility for more accurate results to literature data. By investing more time into these projects, it is possible to create a new methodology for examining chemical warfare agents without the need for experimental data. I would like to acknowledge my NGIT mentors, Dr. Gennady Gore and Ella Ivanova, as well as Dr. Armani and Dr. Makar, for giving me the opportunity to conduct research under the ACS Project Seed Summer Program. Thank you for your time.